Hello, everybody. Welcome to the first lecture of Applied Matrix Theory. Um, we'll explore a lot of different applications of the techniques we'll develop in this course. And all of these techniques are really, they kind of stem from understanding what systems of equations are and how we solve a system of equations. So first, I wanted to start with what is a system of equations. So let's start with a geometric understanding. A system of equations is really representing a family of functions, if you would like to think about it that way. So what we have geometrically, well, let's start with some linear functions. Let's start with, say, well, here. Let's say in red, we have one function, say y equals f of x. And then maybe in blue, we have another function, y equals g of x here. And the geometric understanding of a solution to a system of equations is a solution is where two, or this family of equations, where the point satisfies that all of the functions are the same. So for example, if we were to have, let's say we have a system of equations with two unknowns. So if we have, draw a graph here again, let's say we have the functions or the equations x plus y equals 3 and y minus x equals 5. So if we were to graph these, well, the first one turns into y equals 3 minus x, and the second one turns into y equals 5 plus x. So if we were to graph the first one, let's say we graph it in blue, then we have an intercept of 1, 2, 3, and slope -1. So this won't be perfect here, but you can kind of get an idea. If that up here is 3, this would be 3, and this would be our y equals 3 minus x. Well, then let's say in red, we graph 5 plus x. Well, then we have the intercept of 5 up here, and then it has slope 1. So something like this, and out here would be x equals -5. And the solution to this system of equations, meaning points, so let's write this out, a solution to a system, I'll just abbreviate to system, is points x, y, such that, well, in this case, if in blue we have f of x, and in red we have g of x here, sorry, I forgot to write that this would be y equals x plus 5, well, then a solution to this system would be the set of points x, y, such that f of x equals g of x. And so we can understand solutions to a system of equations purely geometrically. So we could figure out, just by using rise over run, we wouldn't even need to solve algebraically for x or y or anything like that. We could just purely geometrically find that x equals -1 is a solution to this. More explicitly, when x is -1, we would have y is 4. And so in this example here, the point -1, 4 would be a unique solution to this system of equations. Now, systems of equations they're not guaranteed a unique solution. In fact, they're not guaranteed any solution. So let's do some more examples of when a system of, and let's stick with linear. Most of the applications and techniques we'll learn in this course will be dealing with linear systems of equations. And basically what that means is we won't take any variables to a power higher than 1. So this is just variables always to the first power. So we'll be looking at linear equations. So a system of linear equations can have no solutions. For linear equations, the perfect example or quintessential example would be if, let's say, the first function is mx plus b1, and the second equation is mx plus b2, i.e. these have the same slope, but different y-intercepts. These are known as parallel lines. If you have a system of equations where everything is parallel, at least in the setting we're looking at 2 unknowns, and we're also looking in 2-dimensional space right now. So if you have parallel lines as your system of equations, then these systems will have no solutions. Another example would be to have infinitely many solutions. Some examples of when this would be the case. Well, if you had a system of equations, let's say the equation y equals f of x and y equals g of x. Well, if you had that f of x and g of x were the same thing, then these lines overlap. And so you would have a solution for all. So this upside down A is for all. You would have a solution for all x in the real numbers. So here, this epsilon means so it means x is in the real numbers, or I think more precisely, you would say x is an element of. And so again, this symbol here, real numbers. I'll try to introduce some notation throughout the first few lectures, so that basically because I'm lazy and so that I can save some time and shorthand where I can. Another example here is for infinitely many solutions would be to, and we won't really consider these because one of these functions isn't linear, but let's say we had some horizontal line, say like y equals k. Then if we had like a sine wave oscillating and we let k vary, or not k rather, but if you let x vary between negative infinity and infinity, you see you would have an infinite number of solutions, because no matter how far out you go in either direction along the x-axis, you'll always find intersection points between these two functions. So These are examples. Again, these examples we've explored are two variables and or let's just say two variables in 2D space. Well, we need not be so restrictive in what kind of systems of equations we're looking at. For example, we could have 3 variables, but still be in 2D space. So say we have 3 equations here. And a solution, again, I've drawn it to be 0, but let's say this intersection point is at the x value of x naught here. So in this example, x naught is a solution where if we had these labeled like F, G, and H maybe, where all 3 of them are equal. And this is important because it is not enough just to have 2 of them equal. For example, this kind of small change to the previous example here, if you just kind of were to shift the green line up a little bit, you can see there's nowhere where all 3 of these lines intersect simultaneously. Sure, 2 of the 3 lines intersect at some points, but this would be an example of no solutions. So my point is that if you have a system of equations, a solution has to satisfy every, or a point that's a solution has to satisfy every equation, not 3 of the 4 or 2 of the 3, et cetera, et cetera. We can also consider higher dimensional space. Unfortunately, we can only picture up to 3 dimensions. So let's say we're in 3D space with 2 equations. So, and it's linear, right? So these are linear equations. In 3D space, we have multivariable functions expressed as z equals f of x, y, right? And these will be planes. So if you have 2 planes, a linear function in 3D space is going to be a plane. So we can draw, well, I won't draw the coordinate axes. So here we have a plane, let's call this f of x, y, and then we have some other plane here intersecting maybe like this. And so we can call this one g of x, y. And so now you look at the intersection, right? What was the intersection of 2 lines or 3 lines, right? It's always 1 dimension less, right? So a line is 1 dimensional, and the intersection of 2 lines, sorry, I'm getting back to one of these. So here we have 2 1-dimensional objects, right? A line is 1 dimensional. Their intersection is 1 dimension less. So it's 0 dimensional, right? Points, a collection of points would be a 0 dimensional subspace of your overall space, right? And so when we look at planes, we're looking at a plane as a 2-dimensional object, right? There are 2 degrees of freedom. You can move left and right, and you can move forwards and backwards. You can never move up and down in a plane. And so these objects are 2-dimensional, and their intersection is 1 dimension less. So here, the solution set will be a family of points described by the equation of that line, right? So the solutions to a system of equations in, say we have 2 planes here, Well, those are the points x naught, y naught, such that f of x naught, y naught equals, sorry, I'm running out of room, so I'm going to go up and down here, g of x naught, y naught. And this collection of points, x naught, y naught, is going to, these points will necessarily satisfy that they live on this line. Of course, just because we can't picture higher dimensional space doesn't mean we can't still study it. For example, if we were to look at, let's say we're looking in 4D space, and we had 3, or let's say still 2 equations. Well then, sorry, let me use W here. Right? Then functions in this 4D space are, say, W equals f of x, y, z, and W equals g of x, y, z. And these, since we're looking at linear equations in all of our systems, these have a name in higher dimensions. These are called hyperplanes. So basically, this is a 3-dimensional, so maybe, you know, I could draw like something 3-dimensional. This isn't a hyperplane, right? So I should use something that would be linear. Something linear would be maybe like, to us, the projection, like in a lower dimension, it would just look like a cube. And if you intersect 2 cubes, so the picture is really messy here, I apologize. But the point I'm trying to make is the intersection would be a plane. So then you would have a solution set that's 2-dimensional. But what I wanted to do here is mention that we do and can study higher dimensional spaces, even though we can't really picture what's going on. And now, what we want to do is we understand what a system of equations is doing, is it's representing a collection of geometric objects, right? The algebraic analog here is we would have, let's say, A11. Well, the analog here is we have this system of equations, right? So we have like y equals f sub 1 of x, y equals f sub 2 of x, et cetera, y equals f sub, maybe we have m equations, right? The algebraic analog here is that f1, the solutions, are f1 of x naught equals, et cetera, f sub m x naught. And so we understand that the algebraic notion of equality and the geometric notion of intersection are really 2 sides of the same coin here, right? It just depends on how we interpret it. But in terms of solving for these points that give you the solution to a system of equations, we really rely on algebraic methods. So what I want to do now is take a look at some methods. Let's say algebraic tools, or I like methods better, to solving I'll shorthand to system here. So the first is elementary row operations, or sorry, I'm ahead of myself. Let's just look at elementary operations. And these elementary operations. So this is the first one we're going to look at. We will explore two more in the next, well, on Tuesday and then in the next video. So this is today, this video, current. This is for number 2. This will be part 2 of the video, and then this will be covered on Tuesday. We have also, it's called Gaussian elimination. And then we also have Gauss-Jordan elimination. But for now, let's just try to study elementary operations. Okay. So first, let's set up just an abstract system of equations here. So let's say we have so let's let m and n be elements of the integers. So let's just say these are positive integers. Then we're going to let m here denote the number of equations in our system. And then we're going to let n denote the number of variables. So what would this look like? Well, let's call, for every variable, there could be a coefficient, right? So for example, when you're looking at, let me go back here. Well, when you would be looking at something like 5x plus 3y equals 2, and then negative 4x plus y equals 12, right? The numbers in front of the variables, these are called coefficients. And so I'm denoting these coefficients by just a, and then I'm going to use some indices here. So give myself some room. Let's say the first equation is a11 x1 plus a12 x2 plus et cetera, plus a1 n, because we have n variables. So, and then xn equals, and then, okay, sorry, gave myself no room. So let's try that again. And then we'll set this equal to a constant. We'll call it b1, right? And then for the second equation, we would have something like a21 x1 plus a22 x2 plus all the way, and now it would be a2n xn, and then this equals b2. So if you'll notice, the first number of the coefficient is representing what row you're in or what equation you're on. And then the second number is representing your variable spot or what column you would be in, right? And so you keep going, and then we would have a, and there are m equations. So this would be a sub n m1 x1 plus a sub m2 x2 plus a sub m n xn equals b sub n. And so this is going to be our system of equations here. This is a system of m equations and n variables. A shorthand notation for this is to say, write the sum as j goes from 1 to n of a sub I j x I equals, or excuse me, x j equals b I, and j is already running from 1 to n, and then I also needs to run from 1 through m, right? This is kind of a shorthand notation here, but this is representing the same thing. So what we can do to a system of equations is we can add. Well, first, say we can switch the order. So if we had let's say, for an example here, let's say we have x plus 3y equals 5, and then 8x minus 2y equals 10, and 7x plus y equals -8. This system here is equivalent to writing this in any order, right? I could, well, nothing really changes when I flip. Let's say I exchange the first equation for the second equation here. So it's pretty clear that these are equivalent. And when you express them purely algebraically or as equations, this seems kind of trivial. Like, well, of course, right? I could write it up in the corner here and it would still be the same. But once we start representing systems of equations via matrices or a matrix, then this will become a lot more important here. Something else we can do is scale an equation. This means to multiply both sides of an equation by some number. So let's say k, where k is a scalar. And this is for, we're going to be looking for k non-zero. If you're not familiar with the term scalar, that basically just means a number, right? So if you were to have the equation, let's just take x plus 3y equals 5, this equation is equivalent to, let's say we multiplied, if k was 2 in this example, then we would have 2x plus 6y equals 10, right? And so you can do this to any equation that you want, and that won't change the system as a whole, because this is really just the same equation expressed differently. Another thing you can do is you can add a multiple of one equation to another. So let's say we had this system E1 equals B1, E sub 2 equals B sub 2. And so here I'm letting E sub 1 just be like the A11 X1 plus blah, 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 right? Just to save some, some writing. Well, then this system is equivalent to, let's say, we're looking at a scalar k again here. Then let's say we scale the first equation by k. We know that's equivalent to ke1 equals kb1, e2 equals b2, right? We've just seen that this is an equivalent system. And another system that's equivalent is to add a multiple of one row and add it to another equation. So for example, this would be equivalent to the system. Let's replace row 1 by k times e2, or row 2 rather. So if this would be the first row and this would be the second row, then we're going to replace row 1 here, or this first equation, with k times the second row plus row 1. And so what this would be is E1 plus KE2 equals B1 plus KB2. So sorry. This would be equivalent to the system. E1 plus KE2 equals B1 plus KB2. And then we replace the first row. We didn't do anything to the second row, right? So then we would just have E2 equals B2. And so this is another example of an elementary row operation. And one remark I want to make is that there are many methods to solving a system of equations. So if in class, if I ever do an example and I do it this specific way, and then you look at that problem and say, oh, for me, it would have been easier to use this method instead. That's great. You should use what your best at. Okay, so this is where I will break for part 1 of Monday's lecture. And in part 2, we will look at Gaussian elimination and how we realize a system of equations via a matrix. So we will start discussing that in the next video.